Ecco, ci siamo. So the H theorem says the following thing. One starts with a quantity, which is the integral. Okay, so I'm assuming here that the distribution function f is just a function of p and t. Okay, so we work in this specific case just to make the calculation simpler. So uniform in density, uniform with respect to R. Okay, and so the H theorem defines a quantity which is called H, indeed, and which by definition is the integral over dp of f of p t log of f of p t. Okay. Where I remind you that f of pt is the solution of the Boltzmann equation, which was derived among the different approximations, such as the one of dilute gas, for instance, the two-body collisions. But one of the most important, well, for what I'm going to say, assumption is the assumption of molecular chaos. So this function here is a solution of the Boltzmann equation, which was derived by assuming molecular chaos, which means that the two-body distribution, the joint probability, if you want, is just a product of the single particle. So, which means that basically the two probabilities for different momenta are completely uncorrelated. Okay, which is a strong assumption that actually is at the origin of the let's say irreversibility of macroscopic systems. Okay, as we are going to show within the H theorem. Yeah, so basically one defines this quantity, and the H theorem says that the derivative of H with respect to time, because here I'm integrating over momentum, there's no dependence on R, but there is a dependence on T, and the theorem says that this quantity, the derivative of this quantity is less than zero. Okay. And of course, put in this form, it's kind of astonishing because it says that there is a quantity here whose evolution is not reversed, is not symmetric with respect to time reversal, right? Because you define a quantity here that depends on time, and then it decreases monotonously as a function of time. Okay, and at some point it will reach a condition for which the h dt is equal to 0, which is actually the condition of thermodynamical equilibrium. Okay, so this is the statement of behind the H theorem, and we can actually show that this is true by using by doing some little calculations. But let me comment first on one thing, is that this structure that you see here, f log f, is something that we saw already last week when considering, for instance, the Gibbs entropy or the Shannon entropy. Yeah, indeed, there was a minus sign there, because the logarithm of f is if this is a probability distribution, this is less than 1, therefore we define the entropy as having a minus there. Well, indeed, this H, for historical reason, is as Boltzmann defined it, is this quantity, which is basically, apart from a minus sign and some other factors that maybe we will derive later, is basically the entropy. Okay, somehow is let's say a quantity. If you think about entropy as a quantity that is defined only at the thermodynamical equilibrium, as it must be, this quantity basically reproduces the entropy at the thermodynamical equilibrium, but to some extent it generalizes the entropy also in a non-equilibrium situation. Okay, so when F is not F0, which is the solution at the thermodynamical equilibrium. Okay. Yeah, so how to show that this system, this equation is indeed correct, this inequality. The calculation is simple, so then I like to show it. And so basically we start by calculating the derivative of h with respect to time, and by using the definition of h. So this is the integral over dp, and then I have the derivative of f with respect to time, and here I have p t times the log times, well, yeah, okay, I can also do it this way. Times the log of pt plus, now I have to derive the log, so I have f of pt, derive the log, and then I have f of pt, and then the derivative of f with respect to time. Okay, which is equal to, let me close this. This is equal to dp, and then I have the df dt. Let me remove the PT dependence just to write a little bit less, because it's just one black box. Okay, so here I have what I have 1 plus log of f. Okay. Okay, so far so good. So now let us remind which was the Boltzmann equation in the situation we are analyzing here. df dt, I am assuming that there is no dependence with respect to r, which the system is uniform. Also, this I forgot to say, that I am assuming that f is equal to 0, so no external field. And therefore df is equal to df dt control, which is the collision integral, no? by the Boltzmann equation. Okay. The fact that I have or I do not have an external field is not very important, in the sense that if you have an external field, that will basically change the average momentum, will shift the average momentum to a certain value, so doesn't do so much. Okay? And what is the df dt? So the collision integral was the quantity that I can now write directly there. And let me remove also these. And here I can write 1 plus log f. And here I will put, instead of f, the derivative of f, I can put the collision integral, which was the following thing, was dp, okay, which defines the h. And then I have dp2, dp1 prime, dp2 prime, then there was, yeah, the matrix element T, F, E were modulus. Then there is the conservation of energy and momentum. And there was then the, yeah, this difference between F1 prime, F2 prime minus F times F2. I think it's there. Okay, yes. Where F1, F2 prime, and F and F2 correspond to the distribution computed at PT, P2 T, P2 prime T, and P1 prime T. Okay. Okay, so now let's call. Let me see. Let me call this quantity 1. Okay. So 1 is the derivative of h with respect to time, and I have used the fact that I know the structure of the collision integral. Okay. And now let me switch. Take 1. Oh, take 1. And do the following substitution. So we go from P to P2 and from, of course, P2 to P. So I just exchange what is the, well, I'm just switching from P and P2, and you will see the reason for which I'm doing that in a moment. Okay. So let me see what happens now. Okay, so if I do this, then this quantity, and of course, let me comment on this. I can do this because I'm integrating over dp and dp2. So these are variables on which I'm integrating. So there's no reason to have a specific name. No? So I'm integrating over that. In any case, I'm integrating, so I can call P2 and P2, I can call it P. So if I do this, I get a second way to express the derivative of h with respect to time, which is dp, dp2, dp1 prime, dp2 prime. And here comes the interesting part, which is 1 plus log of f2, because I'm switching from P to P2, but it's okay because I'm integrating over this quantity. And yeah, and then this third, well, the rest is basically the same in the sense that T at T delta 4 is the same, delta 4, and also this quantity is the same, no? Because we have F1 prime, F2 prime minus F2. This is symmetric with respect to exchange of P and P2. So then 2 is equal to 1, and therefore I can say that the derivative of h with respect to time is equal to 1 plus 2 divided by 2. Okay? Because they are the same quantity. So then this is 1/2 integral over all the momenta, dp1 prime, dp2 prime. Okay, so then I have the, as usual, the DFP square modulus, the delta 4, and here comes the interesting part, which is, well, okay, so this is the same, so f1 prime, f2 prime minus f2, and then I have the sum of the two quantity here, which is 2 plus the log of f times f, f2 times f, okay? So log of f, f2, okay. is one thing. Now I do another switch, which is the following. Let's take P1 prime and call it P, and P2 prime, let's call it P2. So again, here it's not a problem because I'm integrating over these quantities, and the structure here is invariant with respect to what is before and what is after the collision. No? So I can do this and actually write. Okay, so let me call first this. Let's call it 3. This way to express h, let me call it 3. I do the switch, this one, and I get the following. So 1/2, okay, all this quantity, 52, 51 prime, 52 prime. So this is the same, this is the same. And now here I have FF2, yeah, so here I have F2 minus F1 prime, F2 prime, because I'm switching from P1 to P, so this becomes F and it becomes F2 and the following, and the same for the other term. And what I have there is 2 plus log of F1 prime, F2 prime. Okay, let me check if everything is correct. So 1/2 F2, F1, ok, F1, F2, oh, benissimo. So and let me call this final expression, let me call it 4. Okay, so I have 3 and 4, which again are the same quantity, namely the derivative of h with respect to time. So I can make the following thing and write the derivative of h with respect to time can be written as 3 plus 4 divided by 2. And if I do this, what do I get? 3 plus 4, I have it there, so it's 1/2 and 1/2. I can collect this 1/2 and then factor 1 divided by 4. Then I have this integral, let me write, maybe I write it here, so it's 1, 4. Then I have the integral, d1 prime, dp2, dp2 prime. Ok, vabbè, queste qui sono sempre le stesse, so here fa il modulus delta 4. And so now when I sum up these, let me check, I get a minus, from this to this I get a minus there. No, I can, well, I can put a minus sign here and put the minus there. And therefore, I can actually write F1 prime, F2 prime minus F2. The 2 drops, and then I have the logarithm of FF2 minus the logarithm, so this times the logarithm of F2 minus the logarithm of F1 prime, F2 prime. Okay. So let me now remove these. So then the h dt is equal to 1/4 dt 52 time modulus delta 4, and then I have f1 prime f2 prime minus f2 times the log of ff2 divided by f1 prime f2 prime. And this should be the end of the story, because, yeah, okay, this is the end of the story. So now you see that if f1 prime f2 prime is larger than f2, so this term is positive, whereas this is negative. Okay, so the integrand is negative, because we have a log, and similarly, if f1 prime f2 prime is less than f2, this is negative, but this is positive. And so this is again negative. Okay. So indeed, what we get is that indeed dh dt is less than 0. Okay. So the derivative of this quantity is always negative. So I have a quantity that has clearly kind of error of time, in the sense that defines a specific direction for the evolution of time, which is the one for which h is decreasing. And then at some point, since the h dt as, okay, in the integral as again f1 prime f2 prime minus f2, of course dh dt is equal to 0 implies again that f1 prime f2 prime is equal to f2, which was the condition for obtaining the stationary solution of the Boltzmann equation. Okay. Okay, so this condition is fulfilled when finally f coincides with the f0, which was the solution of this, let's say, the stationary solution of the Boltzmann equation. Okay, so then I see here that the derivative of h with respect to time is less than 0, and then in the limit of t going to plus infinity, at some point this derivative is 0, and when the derivative is 0, the f pt actually is equal to the f0 of t. Okay, and dh dt is equal to 0. So then this H theorem and associated with the Boltzmann equation, so basically provides. Let me say if I see if I have to say something more about that. No. 3, 4, so it basically provides. First of all, an arrow of time, in the sense that it says that this quantity h is decreasing as a function of time. And then when the derivative is eventually 0, that corresponds to the solution f0, the stationary solution of the Boltzmann equation, which we know from last time is indeed the Maxwell-Boltzmann equation for the velocity. Okay, so we start from a system which is out of equilibrium, and in this respect, out of equilibrium now means that the distribution F is not the F0, okay? And equilibrium, thermodynamical equilibrium at a microscopic level means that my system has a distribution of momenta which is the Maxwell distribution, okay? So in this respect, we have now a microscopic definition of equilibrium in the sense that in thermodynamics, thermodynamical equilibrium is clearly just a situation in which the macroscopic quantities are stationary, so like energy, pressure, and so on and so forth. And I know that at some point I will reach this condition. So here, instead, I'm saying that, first of all, if I'm able to solve the Boltzmann equation, I can have an idea on how much time I need to go from F, which is, let's say, my initial F, out of equilibrium, to the equilibrium distribution. So I can get an idea on how much time is needed and which are the processes that drive this tendency to equilibrium. And also I have a definition, a microscopic definition of equilibrium, which is the situation for which the h dt is equal to 0, or if you want, the distribution of particles follows exactly the Maxwell-Boltzmann distribution. In this respect, when you do calculations of systems out of equilibrium, and you want to, let's say, a microscopic description, by using a microscopic description, for instance, molecular dynamics, in which you really take into account the microscopic interaction with particles, and you want to check if your system is or in equilibrium or is out of equilibrium, you basically check the distribution of particles, the velocity of particles, and if the distribution of the velocity follows a Maxwell-Boltzmann distribution, then you say that the system is thermalized, okay? In the sense that it has reached the thermodynamical equilibrium, okay? And also I remind you another thing which is important about this topic is that it says that a system to reach the equilibrium needs indeed some microscopic interaction. They can be even very, very weak, but at some point we need them, okay, in order to reach equilibrium. Otherwise, I would have a free streaming situation in which particles just free stream without interacting, and there's no way for them to talk to each other. So if I have a particle with a certain velocity, it will follow, it will propagate with the same velocity. That's it. Okay. So if I have, for instance, a system in which the velocities of the particles are all the same and in the same direction, okay, this is basically just as a macroscope, as a one particle, is equivalent to a one particle, basically. Okay, there's no entropy. It's not a thermodynamical system. Okay. If I have instead interaction, the particles will exchange momentum, and at some point they will reach this situation. Okay. So now about the H theorem, of course, there is a lot of discussion, and there have been also many numerical simulations to show that this theorem is correct. Well, actually, one has to say that this theorem is also, let's say, statistically, in the sense that if you do really a microscopic simulation with computer and compute this quantity H and the derivative of H, you will not see a monotonous decrease of H. You can have some fluctuation, which H can fluctuate and be also positive. But actually, the overall behavior is really decreasing as a function of time. The fluctuations are due to the fact that in some situations, the molecular chaos hypothesis, which is the one that is behind all of this derivation, is not correct, in the sense that this is an assumption that in most of the cases, most of the time is correct, but it could be, let's say, a little bit more or a little bit less correct, and this could, in principle, change also the sign of the H, but overall, this is correct. Indeed, if you see, I think in the book of Wang, there are some results of simulation of H for a system, and it shows that, Okay, you can have some noise, but at the end, the overall behavior of this quantity is indeed the one predicted by the by the HTR. Okay, and so another comment, of course, is the following: that so behind this HTR, there is a lot of even philosophical discussion about the fact that you get an equation which is this one, which encodes somehow irreversibility, and we have used in this derivation microscopically reversible laws. No? Indeed, TFI, which is a matrix element, is indeed time reversal, but actually we end up with something which is not time reversal. But as I said last time, the reason for that is the very important hypothesis of molecular chaos, which is basically the hypothesis that the correlations that can be established on a microscopic level are somehow washed away as a function of time. Okay, so these correlations are very rapidly lost, and then, well, actually, by losing these correlations, the system can have this degree of irreversibility. Okay. I mean, one thing, maybe I don't know if, because this is an experimental lecture, so but maybe one way to understand how this irreversibility comes out from a microscopic reversible situation is, well, to some extent, I think it's similar to what happens when you do the Monte Carlo simulation in a computer. I'm pretty sure that many of you have followed the course of Tripiccione, no? On complex systems. Yeah, and you probably have talked about the pseudo-random generation of pseudo-random number generation, right? The algorithms.
Sì.
Okay, so if you think about that, also in that case, you have a law which is actually is deterministic, and it is also reversible in the sense that the algorithm for computing pseudo-random numbers are really algorithms. So there is a law there. There is a way, a mechanical way to produce these numbers. But if the algorithm is clever enough, and of course this is the goal of a good pseudo-random number generator, all these numbers that you generate are uncorrelated with each other if the algorithm is very good. Okay, so in this respect, you are generating a random, let's say, list of numbers out of deterministic code. Okay, so in this respect, I think the situation is somehow similar to this one, in which we have a deterministic and reversible microscopic law, which are the law for government B, so the Newtonian law, or it could be also the quantum mechanics when computing a matrix element. And but at the end, the overall macroscopic system is irreversible, and this is due to the loss of correlation. Of course, this does not exclude that at some point, and this is okay, all the discussion about the Poincare time, at some point I have a very big fluctuation that with a very big increase of DHDT. Of course, these are fluctuations. I cannot exclude the fact that there is a fluctuation so big that actually the system in one box is actually localized in a single point of space. But this fluctuation is very much suppressed for what concerns the probability. Okay. So then, if you think about the evolution of a dynamical system as a sort of let's say pseudo-random generation, in which these numbers, pseudo-random numbers are the position and the moment of the particles, it's clear that you will follow an evolution in which the system evolves towards the most probable situation. And the most probable situation is actually the situation in which entropy is maximized, or if you want, age is minimized, okay? Because the two things are basically the same apart from a minus sign, okay? Okay, so I think I will stop with this. This is a very fascinating subject, I think. And let me go on. And in particular, I want to now exploit a little bit the fact that we are now using a statistical approach to macroscopic systems. And let me just remind you what is the Maxwell-Boltzmann distribution, first of all, and how it is connected with macroscopic quantities, such as pressure. And then I would like to do a small exercise just to have fun and just to play with this distribution. Okay. So last time I think we wrote by imposing the stationary condition, we wrote that F0, which is the equilibrium distribution, siamo qua, yeah, so F0, so equilibrium, F0, P is a quantity which is l'abbiamo chiamato C, C è la meno P quadro per A. So where this the fact that it depends on P squared is basically due to the fact that we derived last time a scalar conservation equation, and we know that the scalar quantity that is conserved is the energy. Well, actually, as I said before, I can also well write something like this. Which of course will depend on P squared plus P0 squared minus 2P scalar P0. So in this way, this is more general, of course, and in this way I have a conservation of energy in the equation that we derived last time, a conservation of momentum. So I have a linear dependence on P. Okay, but this is let's say a useless complication on this level, because we can impose that the system has this P0 is basically zero, because this is okay. Of course, this is a Gaussian, right? So then I can impose that the average momentum is zero, and this is of course correct when I do not have any force acting, external force acting on my system. So I can work out, I can work directly with this. Okay. So now the idea now is to find C and A. Okay. And to show that indeed these two quantities, when we find these two quantities, we actually get the distribution that you know, which is the Maxwell-Boltzmann distribution for the velocity. Okay. Okay, so let's start with this. We know that if I have f of r, p, and t, and I'm integrating over r and over p, this must provide the total number of particles, okay? And of course, this is correct also for f0. Now, if f does not depend on r, here I get a volume, and therefore the integral of dp of f of rt is equal to n, where n is the density. So it's the total number of particles divided by the volume. Okay. Yeah. So, and of course, this is true also for dp f0, sorry, this is not r, this is p, sorry, f0 p must be equal to the density. Okay. So then the first equation that I can impose on my system to find the normalization is that the integral over f0 of p is equal to the density. Okay. So n is equal to integral of dp of c a to the minus p squared e to the minus p squared a, which is equal to, so here I have c times 4 pi, then I have an integral from 0 plus infinity dp p squared e to the minus p squared a. Questo è 4pc. Okay, so now this is very typical, and we will find many integrals like this ones. Once you have a Gaussian distribution, and you integrate over p squared, over p cubed, over p to the power 4 or 5. Okay, these integrals are always present in this context. I will not do it. This one can do it by integrate by parts, no? And we just write the results of this. So this tells me that m is equal to 4 pi c, and then the result of this integral is square root of pi, e poi c'è un 4 a to the power of 3 half. 4 pi over c, okay. Okay, so one can do this integral and get this. Now, from this, I get the normalization constant, because then C is equal to n divided n h to the 3 half, and divided by p pi. So C is n, and then I have h divided by pi. Okay. So then my f0 now, by imposing the normalization, is equal to n a pi to the power of 3 half, and then I have, yeah, so e to the minus p squared a. Okay, so now I have to determine a. Of course, you already know which is the value of a, because you are familiar with the Maxwell-Boltzmann distribution for the velocity. So a must contain a fact. Well, it's basically 1 divided by 2m times kbt. Of course, there are many ways to derive the Maxwell-Boltzmann distribution, and I think I will better do it when we talk about maybe the canonical ensemble, maybe, okay. Or well, even if you consider the microcanonical ensemble that we have derived now just for the case of localized and independent systems, there you have the probability of occupation of a single energy level is e to the minus epsilon I divided by kBt. And here the situation is similar, although now is a continuous spectrum, let's say, that we are considering. So we need some to be more, let's say, we need some derivation to extend this microcanonical to the case of independent and not localized systems. And this we will do next week because there are some subtleties there. But in any case, you might remember, or you can just by comparing with the microcanonical ensemble for the case of localized system, you can infer that this H is actually 1 divided by 2 and the KBT, and therefore this will be the E to the minus kinetic energy of the particle divided by KBT, which is the typical thermal energy. Okay, but if you want to just do as a reminder, one way to connect this A to the macroscopic quantities, let me just comment on one thing that you might have done in the course of general physics. So I will just sketch this derivation, okay? So this is the microscopic well, link between pressure and velocity distribution. Okay, so you have done this most probably in the well, few years ago. I will just sketch what is the derivation. Okay, I will not do it fully because it's not that you have seen many times. Okay, so but the idea is the following: so that you have a box, which is the box that contains your system, and you look at this, for instance, surface, and you have a particle, suppose with a momentum exactly orthogonal to the surface, but it is not important actually. You just need the component of the momentum, which is orthogonal to the surface. But anyway, let's take particle that propagates with a certain momentum x before collision. And after collision, we are implicitly assuming that the box corresponds to a potential which is infinite at the surface of the box and is zero inside the box. So I will have a full reflection of the particle with a momentum which is minus px. Okay, it's after the collision. So, collision. Okay. So the variation of momentum of the particles, dpx, is of course now minus 2px. So this is the variation of momentum of the particle. And the variation dpx of momentum of the box, or if you want, of the surface, is just the opposite to px. Okay. So if you want, the particles exchange a momentum, and changes momentum, and this variation is minus 2px, and of course here the variation of momentum instead is just the opposite. Okay. And this 2px of the surface must be equal to the force that the particle exerts on the surface, Fp, so particle on the surface, times dt, which is the period of time that it takes to do this exchange of momentum. Okay. So now force and pressure are related by the fact that the pressure is just a force divided by S. And so for a single particle collision, I can write the 2px is equal to is equal to ps delta t, where p is the pressure and s is the surface. Okay, so I can, let's say, single out the contribution to the pressure of a single particle, and would be something like this. Okay, so this 2px divided by s and delta t is basically the let's say amount, if you want, of pressure that comes out of a single collision with a single particle, so colliding with the surface. Okay. So then, okay, the derivation follows as usual, and I will not, as I said before, I will not derive it again because you told me that you have done this last first year. I just want to write which is the expression for the pressure So the pressure, when I have the possibility to consider the distribution of momentum or of velocity of particle, and I can do it only within a statistical approach, can now be written in these terms. I will write integral, and then I will explain why it's like that. So here I have dp times f0 of p then I have a link constraint on the velocity Vx larger than 0. And let me put it here in Vx and then Vx. Okay, so what I'm saying that this is the pressure on the surface of the box, which is then, of course, is the pressure also inside the gas. Okay, there's no gradient of pressure in thermodynamic equilibrium. And the way I brought this pressure is basically written in terms of this quantity here. What does this quantity? This quantity counts the number of particles, well, not the number, but the density of particles with momentum between P and P plus the P. Okay? Because, yeah, so F0 is proportional to n, so it's a particle density, it's a number of particles divided by the volume. And of course, this counts the number of particles, the density of particles with this specific momentum. And if you multiply these times Vx, then the product of this quantity times this quantity, of course, is a flux, right? Okay. So Vx times density is a flux. And finally, so it's the number of particles per unit time per unit of surface. No? In general, if you do density times velocity, is a flux. And here, this is just the momentum exchanged as due to single collision. Okay. And the other thing that I have to comment is this one, that of course is true because only the particles that have a velocity in the x positive direction contributes to the pressure of this surface. Okay. If we have a particle that travels in the opposite direction, we don't get any contribution. Okay, so I'm going very fast on this because we have done in the past. That's why I'm not spending too much time. Okay? But dov'è che sta? Qui. Well, so let me repeat the interpretation of this. So the interpretation is this, that F0 times dP dimensionally is a density, no? As I said before, because F0 dP times dr is a number of particles, and therefore this dP F0 is a density. I multiply the density by velocity and I get a flux. So number of particles divided by surface divided by time. And then I multiply by the momentum exchanged and I get a pressure. You can check if the dimensions are correct in the sense that this quantity, of course, must be a force divided by a surface. Okay, the surface is hidden in the flux in the sense that I have a number of particles, density of part times velocity. I have a surface. Okay, so you can check out if this is correct from the dimensional point of view. And now, okay, the derivation follows by making some reasonable assumption in the sense that I can actually write that P is equal to dP F0 P and Vx times Px where I'm assuming, and it is reasonable, that the number of particles with Vx larger than 0 is equal to the number of particles with Vx negative. Okay, there's no preferred direction. So then I remove this constraint on the velocity, and I remove this factor of 2. Okay, in the sense that when I remove this and I integrate over all the possible direction of the velocity, and I imagine that I have the same result. This is very reasonable. Okay. And okay, now this again can be written as P is equal to integral of dP at 0 of P, and now I have V squared. Well, I can introduce a mass there, right? And I have a P squared C divided by M, so the mass of the particle. Andiamo qua. So now the pressure is equal to integral over dP of F0. F0 was C, that it was determined in case I will introduce it at the end. Then I have e to the minus P squared A. And then I have Px squared divided by M. Okay, now another thing that one can assume is that, of course, this looks like average over px squared. Now this is a distribution, probability distribution, and this is basically the average. Now this corresponds to px squared average. And again, there's no reason to expect that this is different from the average of py squared and the average of pz squared. Okay, or the system is isotropic. And therefore, I can actually write, instead of px squared, I can write p squared, which is the sum of px squared plus py squared plus pz squared, and add a factor of 1/3 here. Okay. Then let me write here a factor of 2, and then another factor of 2. Sorry, but I have to use the trick of the blackboard. And finally, again, the pressure is this expression there. So it's 2/3 times dp. Then I have c e to the minus p squared a times p squared divided by 2n. Okay. Now, this expression must be compared as with the expression of the internal energy, if you want, because here we see that we have a distribution, probability distribution, times what is the kinetic energy, so that this corresponds basically to the average kinetic energy. And indeed, if I write also the internal energy in terms of microscopic quantities, I can write internal energy divided by the volume as the integral over dp, the distribution function, times p squared divided by 2n. Okay. Because I'm averaging over the kinetic energy, no, and so integrating, if you want, over the kinetic energy of my system. Okay, so now from these two equations, you see that basically the pressure and the internal energy are basically the same, but for a factor of 2/3, u divided by v. So this 2/3 is u divided by v, this quantity. And now, okay, you can use some relation that you might know, you might remember, but we will derive again when we will properly introduce the system of independent and localized and not localized particles. And okay, you might remember that you remember, but we will derive it again, that u for such a system is 3/2 kBt and times the number of particles, and then from this you actually get a normalization, the normalization A. Okay, because here you have the pressure is this quantity here. Then instead of u, I can write this quantity, which is 3/2 kBtn, and by comparing the integral so this integral defining the pressure, this expression that contains specifically kBtn, at the end I can get this this factor of A, which is 1/2m kBt. So don't worry if I do not do the derivation here fully, because I will not ask you, of course, this. And the reason for that is that it's going to be much simpler once we introduce the microcanonical ensemble for the ideal gas. Okay, so it's not. I mean, at this level, it's useless to do this derivation because we will derive it in a more general way very soon. Okay, so in any case, and also these are things that you have done already in the past. So once we have this A, we can write the full expression for my F0. And one way to write F0 is the following. F0 of P. So this is the density, proportion to the density. Then I have the normalization, which contains A, but we have derived now A. And here I have 2m pi kdt, 2m pi kdt to the power 3/2. And e to the minus p squared divided by 2m kdt. Okay, so this is the Maxwell-Boltzmann distribution. Which is a distribution that I get for a gas once I have the possibility to reach thermodynamical equilibrium. Okay, so if I have even very weak interaction, I can my system can go towards thermodynamical equilibrium, then I will get this final distribution. Okay, so this is one way to write it. Another way is the following. Let me see. So if I do F0 of P times dP, now this now counts the number of particles per volume having a momentum between P and P plus dP, and this is equal to n divided by 2n pi kdt to the power of 3/2, and I have e to the minus p squared 2n kdt, and 4 pi p squared dp. And now let me introduce the velocity. So write f0 of p dp divided by n. I'm dividing by n leaves in order to have a probability. And now this is equal to 4 pi, and then I have m squared v squared, 4 pi m squared v squared, and I have the exponential e to the minus 1. Well, let me write that directly, 1 minus 1/2 m v squared divided by kdt. So I'm expressing the kinetic energy in the form of velocity, 1/2 m v squared. What I have here is 2m kdt, 2m kdt pi to the power of 3/2. And then I have another dp, which corresponds to m times dv. So it's an m times dv. I think I have all the possibly all the factors. So then this quantity, which is f0 p dp divided by n, Now this is equal to, if you do the calculations, you can see that there is a m that can be put in. You can collect all the exponents of m, so at the end you will get typical form of the Boltzmann transport, of the Boltzmann, Maxwell Boltzmann distribution of velocity, which is v squared e to the minus 1/2 mv squared divided by kVt, and we have a dv, of course, dv, and then I have a factor here that is kVt to the power 3/2. Then I have a mass to the minus 3/2, and I have a pi divided by 2. Okay. Which is maybe the form of the Boltzmann, Maxwell-Boltzmann distribution you are most familiar with. Maybe, I don't know. So, but the thing one has to remember is that, so this is the probability or the number of particles, depends if I normalize with respect to the particles or not, of having a particle with a velocity, with the modulus v plus dv, okay? And of course, now this equation can be used to do problems in the sense that since I have now a statistical approach, I can face problems which are not, which is not possible to deal with with just a thermodynamical approach. Let me see what time it is. 10:20. So let's try to do some application of this Maxwell-Boltzmann distribution for some problems. Because these I want to stress, which is the, let's say, the power of having a statistical approach. And the problem is the following. So this is a typical kinetic theory problem. So imagine that you have a box containing our gas, and we have a small hole here with a size d, the size of d, size of the hole, which is much smaller than a quantity that is the mean free path that I have not introduced yet, but you might remember what is the mean free path from, you know what is the mean free path, right?
Yes.
Yes? Okay. But okay, I will comment on this in a moment. Okay. So d much smaller than lambda, which is the mean free path, mean free path. What is the mean free path? Well, it's the average distance that a particle covers between one collision and another collision. Okay. So basically, okay. Well, definition clarifies everything, but maybe most important is to remind you that the mean free path is 1 divided by n times cross section, where n is the density of particles. And sigma is a cross section. And so, well, basically, the mean free path, it's very important when dealing with such problems in the sense that if the size of this hole is much smaller than the mean free path, well, if the size of the hole is much larger than the free path, let's start from this, you will have a process of diffusion. Okay, so if D is much larger than lambda, you will have just a diffusion, or if you want, it's just a free expansion. No? Suppose that you have a gas here and you open a big hole here. Well, this is basically the problem of free expansion. Or if you want at the microscopic level, it's just diffusion, in the sense that you will see that at some point particles will cover the whole volume available in that case. No? And in this case, of course, it's not it's very common that 2, 3, or let's say a finite number of particles cross the hole at the same time. Okay. Whereas if you have the opposite limit, so D much smaller than the mean free path, actually this is a situation which is called diffusion. And the diffusion process with respect to the diffusion is different because, as I said before, here basically particles do not have, let's say, do not scatter basically on a length scale of the order of the hole. So basically, if they pass the hole, basically they pass. So how to say? So here, the collision of particles does not play any role. So if they have the proper direction to cross the hole, they will do it. Otherwise, they will not do it. Okay. So it's a process that is very different with respect to diffusion. Okay. And so now the problem is the following. Suppose that this is the direction of Z, and we ask ourselves the following question. To compute dj, which is the infinitesimal flux of particles crossing the hole, and therefore particles that exit this volume. So this is the first thing that we would like to compute. The second thing is the total flux, which is by definition the integral of dj over the velocity. Will be more clear when I will do the exercise. So here I will have an infinitesimal flux, infinitesimal with respect to the modulus of the velocity, and then I can then compute the total flux, so by integrating on the velocity. And then what else we want to compute? Then we want to compute, so this is first, this is second, then we want to characterize the beam, because this basically will be like a beam of particles, and find the average velocity and most probable velocity in the beam. Okay. Another thing that we can compute, but I'm sure that we will have not much time to do it today, is to, for instance, another thing we can do is to compute how the temperature inside the box changes as a function of time. Okay, so we can also introduce some temporal evolution of the system once we have a microscopic statistical approach. So if I have n and okay b and t, I can also compute, but for sure I will not do it today. Come cambia la temperatura, sì, for which is the variation of the temperature inside the box, the function of time, as due to diffusion. Okay. So let me start with the first questions. And right, first of all, this DJ yeah, so let me write it this way. So dj is equal to, so this is a flux. So it's a number of particles divided by surface and divided by time. So it must be something like that. N dimensional, yeah? Time v scalar z, because I need to have these particles. Well, I can have a particles propagating with a certain velocity v, okay? But for counting the flux, what is important is just the z component, okay? Therefore, I multiply v scalar z, okay? And so this dimensional is a flux, where n must be, in this respect, is not the same n as before, must be the number of particles no, questo numero o una probabilità. Maybe this is a probability. Number of particles, I will see now in a moment the normalization. With velocity between v and v plus dv. Maybe it's better to write directly the formula. Maybe it's more clear. Sorry, it's the first time that I do it, so I need to see which is the better way to explain this. Okay, so let me call this as MP. So somehow dimensionally, I want to have V scalar Z provides the component which is necessary in order to compute the flux of particles going outside, okay? And then I just need to multiply this component of the velocity by a density, okay? A density of particles, which will be actually depending on the number, well, not only on the number of particles, or on the density of particles in the volume, but also the velocity. So in this respect, maybe it's better to write this as dn. So maybe this is for the next time, I will write like this. dm. Sorry, I correct it. So dj equal to v scalar z, and then dmp. Okay. So number of particles. Okay, so maybe now if I write the formula, maybe it's more clear now. So Bj, by using now the Maxwell-Boltzmann distribution that we derived before, it's basically the following. I will write the formula and then we will comment. Okay, so this is n, where n is not the same as this one. So n is really the density of particles. So it's n divided by volume. Okay. Then in the Maxwell-Boltzmann distribution, I have a factor of m divided by 2 pi kBt to the power of 3/2, which was l'avevamo scritta così questa, eccola là, sì, è n, sì, c'è un m là sopra, ok, va bene. C'è un m alla 3 mezzi e un kT alla 3 mezzi, ok, dovrebbe essere corretto. So n is the number density. Then I have m 2 pi kBt to the power of 3/2, which was the previous formula that I have there. So, yeah, so it's m 3/2 divided by kBt 3/2. Okay. Then I must be now careful with the solid angle, of course, because now the solid angle is not integrated. Okay. Okay, so let me come back. So this is n. This is okay, a factor of this. Then I have for the exponential, which is 1 m squared divided by kdt. And then I have, in principle, I have dp, which is p squared times the solid angle, which in turn was written in terms of dv v squared times the solid angle. Okay, and now, so this part is now v squared dv, and then I have a solid angle d omega. Okay, so d omega, remind you, is a solid angle. I will see now in a moment why I need to introduce the solid angle, because I'm not integrating over all the direction. Okay, I will do it in a moment, but I cannot integrate over all the direction because some particles which do not have the proper direction of the velocity, they will not escape the hole. That's why I have to introduce the solid angle and then make an integral over the solid angle just for the proper direction of propagation of the particles. Okay. Okay, so let me see what is missing. Yeah, and then I have the scalar product of v scalar z, and v scalar z is equal to the modulus of the velocity times cos theta, where I have introduced spherical coordinates, and here I have my this z, suppose that this is the velocity, and this is theta. So v scalar z is v cos theta. And so let me introduce maybe a v cos theta here. V cos theta. Okay, so maybe now I have all the elements. So density, then I have this m divided by 2 pi 3/2, and then exponential, then I have the dv, v squared, and v, yeah, and then the solid angle, and cos theta. Okay? Okay, so what I've done is to write basically this expression in which I have v scalar z, which is v cos theta, and this d and p is just the Maxwell-Boltzmann distribution. Okay, so it was n times this factor times The only difference is that I'm not integrating over the solid angle, so I do not have a 4 pi here, but I have a solid angle d omega that I will integrate over now. Okay. Okay, so I think it is more or less clear. And the d omega, what is d omega? D omega is a solid angle, and therefore is dp times d cos theta. Okay, so let me write somewhere. Cancello qua forse. Okay, so now let's do the integral over the solid angle. We integrate over d omega. When I integrate over d omega, I have to take dj d omega and integrating this in d phi, with d phi goes from 0 to 2 pi, and this is fine. And then I have dove lo metto questo qua? Facciamolo così. Allora, questo è il dp, poi ho il dj su d omega, che è la quantità che devo integrare, then I have a d cos theta. Okay, now this is the important thing, is that when I integrate over cos theta, well, here I have a dependence of cos theta, no? And where I do the integral is from not from -1 to 1, but from 0 to 1. And this is the important thing. From 0 to 1. Because when cos theta is equal, when theta is equal to 0, and I have to consider just the angle in which theta is equal to 0 and up to pi divided by 2. Okay? Why is such that? So suppose that I have here the hole, and this theta. So of course, to have the proper direction, I cannot integrate from theta 0 down to pi, because all the particles having velocity with negative z components, of course, will not have any chance to exit the box. Okay, so theta must be between pi divided by 2, for which the cosinus is 0, and 0, for which the cosinus of theta is 1. Okay, so that's basically the only thing that we have to change with respect to the isotropic Maxwell Boltzmann. We just need to be careful when we integrate over the solid angle. Instead of putting 4 pi, we have to put 2 pi, which is this integral here, and we have to compute carefully this integral in the sense that we have theta, which varies between 0 and pi half, and not 0 and pi. And also, I have a component, I have a cosinus theta inside this expression that must be taken into account. Okay? Yeah, so indeed, out of this, I will get an integral over dp 0 to pi, and then I have an integral over d cos theta of cos theta from 0 to 1, which is equal to 2 pi for the first one. This is x squared divided by 2, which is 1/2. Okay, times 1/2. So this is 5. So instead 4 pi, I get just 5. Okay? This is at the end, this is the difference between the isotropic case. And of course, this is a flux, and therefore I have, in respect to the Maxwell-Boltzmann distribution, I have an additional factor of J, of V. Okay, so at the end, Dj is equal to M, which is the number of the density of particles, pi, which is this factor here, and then, okay, I have M divided by 2 pi kBt to the power of 3 half, poi c'ho la mia esponenziale, v squared divided by kBt. Then I have here, I have, instead of v squared, I have a v to the power of 3, because I'm calculating a flux. Okay, so it's a density times velocity, and this is dv. Okay. Okay. So now this represents the infinitesimal flux, infinitesimal with respect to the modulus of the velocity. Okay. So this is the infinitesimal flux across the whole. Okay. Bene, questo dovrebbe essere corretto. So now if I want the total flux, come qua non sarà mai. If I want the total flux, I just need to integrate over the velocity. So then the total flux J is the integral from 0 to plus infinity of dj dv, which is n pi m divided by 2 pi kBt to the power of 3 half. Then I have, yeah, I just have the integral now of v squared. Okay. So now I have the integral from 0 to plus infinity of dv v cubed exponential of minus v squared divided by kBt. And that's it, right? So n pi is there, the coefficient is there. Okay, so now let me do the following trick. So I multiply by 4 pi here, and I divide by 4 pi. So this is equal now to, I take out this 4 pi, and I simplify with this, and I have 1/4 n. And what is the expression that is there? Let me write it explicitly. It's m divided by 2 pi kT to the power of 3 half times the integral 0 dv 4 pi v cubed exponential is exponential. Now, what is this quantity? This is basically just the average velocity when you have a Maxwell-Boltzmann distribution, the average velocity in the bulk, not in the beacons, okay? Which is basically just the integral over the Boltzmann distribution of v squared, not v cubed, because I have a v squared coming from the spherical coordinates times another additional factor of v that allows me to compute the average density. Okay, so this is basically just the average modulus of the density of velocity, sorry, of velocity in the bulk. What means in the bulk means inside the box. Okay, where the distribution is a Maxwell-Boltzmann distribution, just integrating over a probability distribution function dv squared dv v squared times v. Okay, so then what I get is the flux J crossing the hole is just 1/4 mv, where v is the average bulk velocity. Okay, so across the hole. Now, the only difference with respect to the case of a large hole in which I have diffusion is the factor of 1/4, because this factor of 1/4 counts the situation that I'm actually considering that the particles must have a proper, let's say, the direction is somehow must be the correct direction in order to cross the hole. Whereas if I have diffusion, since really close to the hole, since it's very large, I will have a lot of collisions. At the end of the day, the flux along the flux for a large hole will be just the normal flux, which is n times the average velocity. Okay. So here, this factor 1/4 comes from clearly from the integration over the solid angle, which is restricted in this case. Okay. Now we will do some characterization of the flux of particles that are in the beam later on. But let me remind you which is this B bar, and compute B bar. Which is, as I said before, the average modulus, so the average of the modulus of the velocity inside the bulk. Okay, so these are m divided by 2 pi kBt to the power of 3/2. Then, of course, I have a 4 pi. Then I have an integral from 0 to plus infinity of x cubed e to the minus alpha x squared, where I have indicated with x, of course, just the velocity, and alpha is a constant, which is m divided by 2 kBt. Okay, so this kind of integral appears when computing the average velocity. Now, this can be done again by parts. I will not calculate these. If you do it, you get a factor of 1 divided by 2 alpha squared. And therefore, the average velocity is m divided by 2 pi kBt power of 3/2. Poi c'ho un 4 pi. And then I have this 1 divided by, so 1/2, and then I have 1 of alpha squared, which means 4 kBt squared, 4 kBt squared divided by m squared. Cioè sono che poi deve cominciare da già. Okay. Yeah, so this should be correct now, and you get a typical result, which is the following. So it's kBt times 8 divided by m pi. kBt 8 m pi. This is the average velocity, the modulus of velocity in the bulk. So you've done this relation, avete fatte queste cose?
Io personalmente non mi ricordo alcun corso dove le abbiamo viste.
Quindi diciamo che la Maxwell-Boltzmann l'avete vista, però non ci avete giocato molto, questa è la questione, vero?
Esattamente.
No, esatto.
Ok, vabbè. Perché diciamo che, non so se avete capito, ma a me piace abbastanza questa cosa, e quindi la sto facendo, però appunto non sapendo se l'avete fatta, quindi non so quanto andare nel dettaglio. So one thing, of course, when you have a Maxwell distribution, which of course it's a very important topic because, for instance, well, in the field that I'm expert on, so for instance in stars, so typically you have Maxwell-Boltzmann distributions. For instance, in the sun, typically you treat the gas by assuming a Maxwell-Boltzmann distribution. That is very important, for instance, when you deal with processes of nuclear processes of fusion. You might remember the gamma peak is obtained indeed by somehow convoluting the Maxwell-Boltzmann distribution of velocity, which is important, of course, for computing the probability of crossing a barrier, and in that case, the barrier which comes from the Coulomb interaction. So one thing about the Maxwell-Boltzmann, of course, is that now this is the average velocity, and this does not correspond to the velocity with the maximal probability, because of course you see that the distribution is not just an exponential. Is this guy here, v squared kT, and there is a factor of v squared here that makes this Gaussian being asymmetric, and then you can try, if you want to compute, then we will do it next time, which is the value of the maximum probability of the velocity having the maximum probability. Okay, you can try to compute this, for instance, in the bulk. And you can try, well, but we will sketch it next time. I mean, it's just computing integrals, basically, so it's not very complicated. You can try to compute the average velocity, V, and the most probable velocity, Vp, also in the beam. And compare it with the ones in the bulk. So you will see that the average velocity and the most probable value are larger. And in turn, this means that in the fusion, basically it's a filtering of high velocity particles. And indeed, there is a tool that is used, for instance, to separate different chemical substances, in the sense that the larger the mass, the smaller the velocity. So you can extract light elements, if you need elements or heavy elements, by just putting a small hole, and this small hole will select the high particle, the particles having high velocity. Okay, so we will come to this next week. Quindi va bene se faccio delle applicazioni di questo tipo, non le avete fatte? Questo era il mio dubbio.
Va bene.
Ok, cioè l'importante è che non le avete viste, poi che siano interessanti, quello purtroppo per voi lo decido io. Quindi...
Abbiamo visto qualcosa in cosmologia, ma molto diverso, nel senso che applicazioni di tipo diverso.
Ok, sì, diciamo che a me la cosa che mi preme, come dire, stressare è che chiaramente se uno ha un approccio di tipo statistico, sono cose che cioè sono tipi di conti, di problemi che non si possono analizzare chiaramente in termodinamica, quindi diciamo a me interessa stressare che in meccanica statistica si possono chiaramente fare molte cose in più rispetto alla termodinamica, perché abbiamo delle distribuzioni di probabilità che ci permettono di fare un bel po' di conti in più. Va bene, allora la prossima volta riprendiamo da questo e vi lascio che già ho sforato un po', ok? Arrivederci.
Arrivederci.
Saluto.
Arrivederci.
Dunque, io devo togliere. Luciano, sto uscendo,